The final topic for this unit is probability. You had some probability last year, so some of this will probably be review. Let's talk about the basic vocabulary first. Probability is the likelihood that an event will occur due to chance. It's usually a number between 0 and 1. It's expressed either as a fraction, decimal, or a percent. And I've written some options here. The probability of 0 is that it's impossible. A probability of 0.5 or 50% means it's going to occur half the time. A probability of 1 means the event is certain. So now let's talk about outcomes. Outcomes are the total possible results, or what I like to term as the total. Look at this die. There are 6 possible results you could get if you throw that die. So the total would be 6. Favorable outcomes are the outcomes you are considering. I like to think of them as what you want. For instance, if I'm interested in the probability of throwing an even number on that die, the outcomes I'm considering, or what I want, is 3. So now, theoretical probability, or the probability you get when you compute probability mathematically, is computed by the general formula, what you want over total possibilities. So, for instance, the probability of throwing an even number on a die is what I want, 3, over total possibilities, 6. That's equal to a half, or 0.5, or 50%. So there's a 50% chance that I'm going to throw an even number on that die. Let's look at this other example. What's the probability of selecting a T from a bag of letters that contain my last name, Serretta? What I want is a T. There's 2 possibilities over total possibilities of 8. That reduces to 1/4 or 25%. So the probability that I would pull a card having a T from a bag of letters containing my last name is 25%. Let's look at this final example of theoretical probability. You toss 2 coins. What is the probability that one will be heads? There are 4 possible outcomes. Heads, tails, heads, tails. What I'm interested in is throwing heads. 2 possible heads out of 4 total outcomes. 1/2, 0.5, or 50% chance of throwing heads. In addition to theoretical probability, there's also experimental or observed probability, and that's probability computed using the results of an experiment or real-life events. For example, last January it snowed 7 days, it was sunny 18 days, and it was cloudy 6 days. So based on that real-life information, what's the probability that it will snow on a randomly chosen day this January? So what I'm interested is snow days. So 7 snow days out of a total of 31. So that's equal to, using a calculator, 0.23, or there's a 23% chance we're going to have a snowy day in January. That's experimental or observed probability because I'm using real-life data or results of an experiment to compute that probability. Now let's talk about the probability of compound events. Compound means more than one. Independent events are two separate events not related to each other. If you are interested in the probability of independent events, both or all the probabilities must occur, and you will usually see the word "and" in the problem. For instance, rolling a die and flipping a coin, or the probability of pulling a card from a deck, replacing it, and pulling another card from the same deck. When you're computing that probability, you multiply all of the probabilities together. So for example, what's the probability of rolling a 6 on a die and tossing heads on a penny? Well, the probability of rolling a 6 on a die, what you want is 1 out of 6 possibilities. The probability of tossing heads on a penny, what you want is 1 out of 2 possibilities. You're going to multiply both those probabilities together. You're going to get 1 12th. And when you use a calculator, 1 divided by 12, that's 0.08 or 8%. Let's look at another example. A card is drawn from a standard deck of 52 cards. It's replaced, and another is drawn. Those are two independent draws. Find the probability if the first card drawn is a king and the second card drawn is an ace. The probability that the first card drawn is a king is 4 out of 52. The probability that the second card drawn is an ace is also 4 out of 52. So if you multiply both of those, I'm going to cross cancel here. Check this out. We're going to get 1 over 169. Pretty slim chance that's going to happen. When you use a calculator, that equals 0.0059 roughly. Or, what percentage is that? Move the decimal place. 0.6% or 0.6%. Let's look at dependent events. Dependent events are two separate events where the behavior of one affects the total outcomes of the other event. Let me repeat that. Dependent events are two separate events where the behavior of the first event affects the total possible outcomes of the second event. Pulling a card from a deck and not replacing it is a really good example of this. We still multiply the probabilities, but we have to take into account the new conditions of that second total. Let's examine the same example, but we will not replace the first card. So here we go. A card is drawn from a standard deck of 52 cards. It's not replaced, so that means the deck will then contain only 51 cards. Find the probability if the first card is a king and the second card is an ace. So, the probability of pulling a king is 4 out of 52. If we don't replace that card, we will now only have 51 in our total deck, so we'll only have 51 total possibilities. The probability of pulling an ace will be 4 out of 51. So we'll multiply those probabilities. I'm going to cross cancel here. We'll have 4 over 663. We'll get 0.006, 0.006. That's 0.6%. So you can see how the total of that second event was affected by the first event. That's why these are dependent events. Now we need to consider mutually exclusive events. They are events that cannot happen at the same time. Usually the language of the problem will have an or in it. So let's look at an example to see if that helps clear it up. Consider the six-sided die. What is the probability that you will roll a 1 or an even number? Now, I am interested in throwing the 1 or an even number. Both of those results would be okay. Both of them are acceptable. I will add those probabilities since both are acceptable. Now, those events cannot happen at the same time. Either one or the other is going to happen. So the probability of rolling a 1 is 1 out of 6. That could happen, or the probability of throwing an even number is 3 out of 6. Since both of those are acceptable, I'm going to add them. So I'll get 4 6, which is 2/3, which is 0.67, and that's 67%. So there's a 67% chance that I will throw a 1 or an even number. Let's look at the deck of cards. What's the probability of pulling a king from a standard deck of cards or an ace? So here again, if I pull a king, it'd be okay. If I pulled an ace, it would be okay. Now those events cannot happen at the same time. It's going to be either one or the other, but both of those probabilities, both are acceptable. So since both are acceptable, I'm going to add them. So the probability of pulling a king from a standard deck of cards is 4 out of 52. Or pulling an ace, 4 out of 52. So pulling a king or an ace, it's 8 out of 52, which is 0.1538, or roughly a 15% chance that I'll pull a king or an ace. So you see how saying or gives me a greater probability of something happening. So it's about looking at the problem for the or, which you add the probabilities, or looking at the problem for the and in that case, with an and, you'll multiply the probabilities. Finally, let's consider combinations. To compute the total combinations, you multiply the totals in each category. Let's look at Benchwarmer's menu. Let's pretend that Benchwarmer sells 8 different kinds of subs, 5 different bags of snacks, and 3 different types of drinks. How many possible combinations of subs, snacks, and drinks can Benchwarmers provide? So there are 8 possible subs that they sell and 5 different types of bag snacks and 3 different types of drinks. So 40 times 3. So there are 120 possible combinations that they could provide. So now how would you make a tree diagram to illustrate these total possible combinations? So okay, I've drawn these different subs. So let's show a tree diagram that will lead us to the total 120 combinations. So here are our 8 different subs. For each sub, there are 5 possible bags of chips. So there's 5. And then there's 5 coming out of that sub. think you're starting to get the picture. And out of that sub, there's 5 possible chips, and so on. Out of each blue line that represents a bagged snack, there are 3 possible drinks, 3 possible drinks, 3 possible drinks. It's getting tight. 3 possible drinks, and 3 possible drinks, and so on. So for this sub alone, you can see I have 15 combinations. I'll skip that for room, sake of room. If I go to this one, I'm going to do the same thing. For each bag of chips, there are 3 drinks, 3 drinks, 3 drinks, 3 drinks, 3 drinks, for 15 combinations off of that sub. And so you would continue on in this manner, and in the end, you would see that you would have 15, 15, 15, 15, 15, 15, 15, 15 for each sub, for a grand total of 120 total combinations. So I've listed an assignment here for you to do. I want you to finish making this tree diagram on a separate piece of paper. You can use S for subs, C for chips, D for drinks. That's fine. Then I want you to go to your textbook and do a few problems. On page 117, I want you to do those few problems. Page 118, I want you to do these 4 problems. Bring this assignment to our next class. But before you sign off, I'd like to do the following problem. So get out a piece of paper and do this following problem with me. Let's use some specific items in this next example. Let's say a sub shop offers a ham sandwich and a turkey sandwich. They offer chips, Fritos, and pretzels. And then to drink, they offer water and Gatorade. I'd like you to make a tree diagram of all the possible combinations or all the possible menus that they can offer. Use my abbreviations in blue. Let's pretend a sub shop offers the following menu: a ham sandwich and a turkey sandwich, chips, Fritos, and pretzels as the bag snacks, and then to drink, water and Gatorade. I'd like you to take a piece of paper and make a tree diagram using these abbreviations in blue on your tree diagram. Take a minute, draw it out yourself before going on to the next screen. Take a minute to make your tree So okay, did you do this? They offer a ham sandwich and they offer a turkey sandwich. For the ham sandwich, a customer can choose the chips, the Fritos, or the pretzels. If they choose a turkey sandwich, they could also then choose the chips, the Fritos, or the pretzels. So there's the first order. If they choose a ham sandwich and chips, they could then either choose the water or the Gatorade. If they choose Fritos, they could choose the water or the Gatorade. If they choose the pretzels, they can choose the water or the Gatorade. So those are all the possible combinations under the ham sandwich. Likewise, if they chose the turkey sandwich and the chips, they could choose water or the Gatorade. If they did the Fritos, water, Gatorade. If they chose pretzels, water, or the Gatorade. Using the mathematical calculation for total combinations, there are 2 possible sandwiches times 3 possible bag chips times 2 possible drinks for 12 total possible combinations. And you can see them on the bottom row. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now I'm going to erase this so I have more room, and I want to ask you a few questions, and I want you to use your tree diagram to answer them. So, okay. Number 1. What's the probability of choosing an item or a menu item that contains water? What you want is 6 out of a total of 12 is 1/2. I hope that's what you got. What's the probability that a customer will choose a menu item that contains pretzels? Well, 4 items contain pretzels. These right here and these right here. So 4 out of 12, which is 1/3. What's the probability that a customer will choose a menu item with pretzels or an item with Fritos and water? So, pretzels or Fritos and water. The probability of choosing a menu item with pretzels is right here and right here. So that's 4 out of 12. The probability of choosing Fritos and water is right there and right there. So that's 2 out of 12. And since I said pretzels or Fritos and water, that meant both of those options were okay. So since both were okay, I'm going to add, and that's 6 out of 12, or 1/2. And if you look at what I have underlined or circled, 1, 2, 3, 4, 5, 6, I'm showing the 6 out of 12 possibilities. Those were mutually exclusive events. I'm only getting one menu item. It's either going to have pretzels or it's going to have Fritos with water. Mutually exclusive. Cannot happen at the same time. What's the probability that a customer will choose a menu item that's not Fritos? Menu item that's not Fritos. So let me say that again because that just wrote all over the old tree diagram. What's the probability that a customer will choose a menu item that's not Fritos? Not Fritos, not Fritos, not Fritos, not Fritos. So what I want, 8 out of 12, 2/3. Okay, that's it for the probability lesson, so see you in class. Okay, let's look at this sample menu. Question number 1. What's the probability of selecting a turkey sandwich? Take a minute, you decide, and I'll write the answer. I hope you wrote 1/3. Question number 2. What's the probability of not choosing a bag of popcorn? Take a minute, you make a choice. I hope you chose 3 out of 4. Question number 3. What are the total possible combinations that this restaurant can provide? Did you get that? 48 total possible combinations. Multiply the totals from each category. Fourth question. What's the probability that someone will choose a ham sandwich, a bag of chips, and a water? A ham sandwich, a bag of chips, and a water. Those are three independent events. Probability of a ham sandwich is 1/3 times the probability of a bag of chips is 1/4 times the probability of choosing a water is 1/4. So the probability that someone is going to choose a ham sandwich, a bag of chips, and a bottle of water is 1 out of 48. So how'd you do on those?